NPSH calculations. For those of you that have been following James and Pleasant's company, we have a whole hour session online on YouTube on how to do NPSH. So we're going to hit this fairly quick, but I encourage you, if you want to go deeper into NPSH, go online to JMP, research NPSH, and you'll pop up with a more detailed seminar. But basically, the system Syzer allows you to calculate the available NPSH. Yes, it does. What are we trying to do here? We've got a little chart to the right-hand side. We want to know what the available net positive suction head is, because if we don't have enough, the top chart on the right-hand side shows the pump working okay. The suction pressure did not drop down below the vapor pressure, so we got no bubbles, we got no cavitation. The bottom chart shows the pressure drop falling down below the vapor pressure, and we're creating gas bubbles and we're cavitating the pump. In other words, there's a pressure drop between the suction flange of a pump and the eye of the pump impeller. And that's what we got on this graph on the right-hand side. We've got to measure the pressure. That piece of this is the gauge pressure, the suction flange gauge pressure. And it pump flows from the gauge pressure to the eye of the impeller, and because we're changing flow rates and we're putting work to it, the pressure actually drops before it hits the eye of the impeller and starts going back up. And that pressure drop of a pump is the defined required NPSH of a pump. And that pressure drop, if it falls below the existing vapor pressure, will cavitate a pump. So how do we calculate what the available NPSH is so we make sure it's greater than the required? How do we make sure that our available NPSH-A is higher than NPSH-R? So here we go, my little chart I just talked about. I want to make sure I never let the pressure drop, the required NPSH in my pump, dip down below the available pressure, and I cavitate. So the bottom chart shows cavitation, the top chart shows the available greater than the required. And this is pretty much the message of what we're trying to accomplish. Let's go back to the same example I just had. Let's go back. So if I pick the green star, what is the available NPSH at that point? The NPSH required is down at the bottom. So all pump curves have on them the NPSH-R, the required NPSH, the actual pressure drop from the suction flange to the eye of the pump impeller. In this case, at 650 GPM, I'm reading over the right-hand side about maybe 8 or 9 feet required NPSH in feet. You also have meters on it if you want it. So now you've got the required NPSH of my 1510 pump. What is my available NPSH? I have to make sure that my available NPSH-A is higher than the 8 feet required. How are we going to do that? It's a simple little formula. I'm sure you worry about this all the time, but we're going to make it easy for you. It's a simple little formula that basically says absolute pressure at liquid surface level. Let's talk about a coolant tower. So that'd be 0 PSIG. It's got to be an absolute. An open coolant tower. So it'll be 14.7 pounds absolute sea level is the pressure on the surface liquid. What is the elevation of liquid above the pump? So that if that coolant tower is elevated above the pump, then we can add that to our available NPSH. It helps us. What do we lose? What's the H of F? How much is the friction loss? What's the friction drop between my coolant tower and the suction flange of my pump? That's taken away from my available NPSH. So you don't want any strainers, anything in there. You don't want any high pressure drop to take away from the available NPSH. Last piece is, what is the temperature of the liquid I'm pumping? What is the vapor pressure of the liquid I'm pumping? How low can I let the pressure go before it cavitates is the question. Those two numbers will wind up giving you the net available NPSH. Now we've got a way to calculate it on the system Syzer that makes it a lot easier than having to run through this formula. So let's go back to our coolant tower. Remember a coolant tower? Let's just take a quick look at it. Same example we just have. Let's calculate what the available NPSH-A is on this tower. Let's take a crack at it and see if we can do this real quick. We got a pipe size. We've already gone into it. It's 250 GPM 4-inch pipe. Look at the elevation. We got to know the elevation of the cold water liquid above the suction pump. So in this case, it's 3 feet. The vertical elevation of the cold water, minimum cold water level in our tower above the center line of our pump, and that's 3 feet. There's one 90-degree elbow in the suction pipe. I'm not worried about total pump head here, ladies and gentlemen. I want to know the pressure drop in the suction pipe into the suction flange of my pump. All I'm looking at now is the suction flange of my pump. That's what I'm interested in, just the suction flange. There's only one 90-degree elbow in there. The suction pipe length is 12 feet. Notice I'm not at Myrtle Beach. I'm at 2,000 feet elevation, so my elevation is up, and that's going to reduce the absolute pressure available from the atmosphere. It's going to be lower than 14.7 pounds absolute, and this is going to take care of it. I've got a suction diffuser, EE-3, and I'm going to use leaving cooling tower water at 85 degrees because I'm pumping cooling tower water at 85 degrees. And when you're doing NPSH calculations, that water temperature is critical because that gives you the vapor pressure of the liquid you're pumping. So you got all that information. Let's go see what we do with it. First thing is we go to the menu and we input 85-degree water. We're pumping 85. We need that vapor pressure. This takes care of it. As a matter of fact, if you haven't noticed, look at the bottom there. It gives you the vapor pressure, 0.6 pounds absolute. If we keep the pressure on 85-degree water above 0.6 pounds absolute, it went overboard. If we let the water pressure get below 0.6 pounds, it will. So that's the message of that water temperature. It's so critical, and we're going to calculate that for you. What size pipe? Go to the pipe chart. We already picked a 4-inch pipe for 250 GPM, and we go back to our relationship with the TEL, and we get our head loss calculations. In other words, 4-inch pipe is 3.35 feet per 100, remember? But we're only worried about the pressure drop of the suction pipe. So the TEL pipe run, we're only using 12 feet. Top right-hand side, we plug it in 12 feet because that's just the length of the suction pipe, 12 feet. How many elbows do we have in the suction piping? 1. How many gate valves? 1. How many pipe exit? 1. Did we have a triple duty valve? No, there's no triple duty valve on the suction side, but there's a suction diffuser, there's an EE-3, so we plugged it in. So if you kind of got the idea, we're just trying to calculate the pressure drop on the suction piping only. That's all we're trying to do here. And that turns out to be 2.55 feet. Very low number, but remember we're dealing with the available NPSH on a pump, and we've got to know what that number is. So it's 2.55 feet. Next, we swing over to NPSHA System Syzer logo, and you see it. We clicked on NPSHA. We're trying to calculate the available NPSH, and we plug in. First thing we do is we look at, is it an open system? It is. Is the cooling tower above the pump? Yes. So we click the very first one. Open system, inlet above the pump. Then we go to location elevation. Is it at sea level? No, it's 2,000 feet up. All right, so we plug in 2,000 feet. Pipe friction loss came over from the previous chart. It's already there for you, 2.55 feet. It came over from the previous scale. What is the dimension for Z? 3 feet. The higher you raise your cooling tower, the more available NPSH you got. The lower your cooling tower, the less available NPSH you got. In this case, we got 3 feet. Left-hand gray chart shows you the available NPSH is 30 feet, which is very high. We only needed, what, 8 or 9? We got 30, so available NPSH is greater than required. We're fine. What a nice, easy way to accurately calculate NPSHA. Beautiful way of doing it. Ladies and gentlemen, we appreciate your time. Remember, this Windows-based version of the system size and the little iPhone versions are online and they're free. For you old guys like me, and I'm an old guy with gray hair, I do like that manual system sizer. The limitation of the manual system sizer is it's only good through 12-inch pipe. Another limitation has nothing to do with NPSH on it. So I would strongly recommend you guys get the Windows-based versions and you spend some time with this. You cannot find a more important tool for every engineer, every contractor, every young person coming this industry to learn. You need this desperately. Have a great day. Thank you for your time.